And we're on.
Okay, so this is the set of topics that will be on the test. Okay, it starts with sequences, determine whether they converge or diverge. Then we have the sum of some series. We have geometric series, another geometric series, and a telescoping sum. Then we have to state whether the series converges or diverges. You have two answers to each of these questions. A, converges. B, diverges. Then, we have three alternating series, and what you have to do is determine whether the series converges conditionally, converges absolutely, or diverges. Then we had two power series, where you have to determine the radius of convergence for each of the two power series. And then you're going to do a Maclaurin series for sine or cosine, one of our two alternating series, and do an approximation for the sine of 1/2 by using the first two non-zero terms, and then determine the error in the above approximation. And what that entails is finding the next term. So that's an outline for the test. Now let's go through this. The first one was the nth term of the sequence is n over 2n plus 1. It converges to 1/2. Take the limit as n goes to infinity. As long as the sequence's nth term has a limit, finite and real, the sequence will converge. So this sequence converges to 1/2. This sequence, however, does not. It diverges because it goes negative 1/2, positive 1/2, negative 1/2, positive 1/2, and there is no limit. This converges to 0 because as n goes to infinity, 1 over 10 to the n will clearly go to 0. So that will converge to 0. The geometric series, the ratio r is negative 1/2. Since its absolute value is less than 1, the series will converge. The sum will be a over 1 minus r. A is 1. The r is negative 1/2. Therefore, the sum is equal to 1 over 3/2, 1 minus and negative 1/2, or 2/3. The fifth one is another geometric series. If you write out a few terms, start at n equals 0. We'll have 1 plus 0.2 plus 0.2 squared, 0.2 cubed, etc. Geometric series where a is equal to 1, r is equal to 0.2, and the sum is going to equal 1 over 0.8 or 5/4 when you simplify it. Okay, the next one was a telescoping sum, where we're going to use partial fractions to rewrite this term, these nth terms. Solve for a and b using partial fractions, multiply by n plus 1. Let n equal negative 1. Negative 1 plus 3 is 2. A is 1/2. Solve for b, multiply by n plus 3. Let n equal negative 3. Negative 3 plus 1 is negative 2. You get negative 1/2 for b. That enables us to rewrite this term as the difference of these two terms. Well, the thing to do here is take the 1/2 out front, and then write out a few terms of this difference. Start n at 0. When n starts at 0, you get 1 minus 1/3. That's what this is. This 1/2 is from out here. Then when n is 1, we get 1/2 minus 1/4. That's this one. When n is 2, we get 1/3 minus 1/5. That's this one. The next one, when n is 3, is 1/4 minus 1/6. It continues in the same manner. Okay? What happens is the 1/3 will cancel, the 1/4 will cancel, everything cancels in the middle. You'll be left with the 1 and the 1/2 from the beginning. At the end, you're going to be left with two terms, but they go to 0 as these number of terms go to infinity. They're irrelevant. The sum of this series is 1/2 times the sum of 1 plus 1/2, or 3/4. Now, on the series, number 7 is 1 over n. It's a diverging series. It's a harmonic series. The difference in degrees is 1, not sufficient to cause the series to converge. It's a diverging series. It's a p series where p is equal to 1, which means it diverges. You could prove it with an integral test, any number of ways, actually. It diverges. Difference in degrees is the bottom line. Difference in degrees is 4, good enough to converge. As long as the difference in degrees is greater than 1, it will converge. This converges because n factorials increase faster than exponential forms. As long as this is increasing much faster than this, these terms will go to 0 quickly enough to cause the series to converge. Number 9 converges. Number 10, however, diverges because that term does not go to 0 as n goes to infinity. It goes to infinity. If the terms are going to go to infinity, the series will diverge. Number 11, 5 to the n is exponential form, n to the fifth is polynomial. Exponential forms increase faster than polynomials. Therefore, these terms are not going to go to 0. They will go to infinity, causing the series to diverge. Number 12. 12, we have n to the 3 halves, or n cubed plus 10. The difference in degrees is 3 halves. Good enough to cause the series to converge, as long as the difference in degrees is greater than 1. This series, we have factorials over exponential forms. Factorials increase faster than exponential forms. Therefore, the terms are not going to go to 0. Okay, and that series will diverge. 14. We have an alternating series. The thing to do is test the positive series first. This positive series, 1 over n squared plus 1, converges. Difference in degrees is 2. Since the positive series converges, the alternating series converges absolutely. 15. The positive series diverges. Okay? Difference in degrees is only 1/2. But the terms are decreasing, and the nth term is going to 0. That's good enough to cause the alternating series to converge. Therefore, it converges conditionally. Its positive series diverged, but the alternating series converged. And the last one, the nth term is not going to go to 0, causing the series to diverge. The series diverges. 17, you need a radius of convergence for the power series. Generally speaking, the thing to do is to use a ratio test and take the limit of the n plus first term over the nth term. And you'll notice that for any given x, as long as n is going to go to infinity, this will be 0, which is less than 1 for every x. Therefore, the radius of convergence is infinity here. Converges for all x's. 18. 18 is, one way to look at this is as a geometric. First thing to do is to move it back so it's centered at 0 instead of 5. That does not change the radius of convergence. And it's easier to analyze. So let's look at this series instead of this series. They have the same radius of convergence. Okay? Well, it's geometric. X over 5 to the n is geometric. In order for this to converge, x has to be between -5 and 5, making the radius of convergence have an absolute value less than 1. Therefore, the radius of convergence is 5. That's one way to do it. Generally, though, you want to use a ratio test, and if you use the ratio test, you will see that, yes, indeed, x has to have a value, an absolute value less than 5, so the radius of convergence is 5. 19. We're using sine x, Maclaurin series expansion for sine x. Sine is an odd function. Therefore, all the exponents are odd. We're going to use the first two to approximate sine of 1/2. Put a 1/2 in here, a 1/2 here, cubed over 3 factorial. That's 1/8 over 6. That's 1/48. The estimate for sine of 1/2 would be 1/2 minus 1/48, which is 23/48. How good an estimate is that? Well, the error, the absolute value of the error is going to be less than or equal to the next term. When x is 1/2, it's 1/2 to the fifth over 5 factorial. That's 1 over 32 over 120. That's 1 over 3840, 3,840. That's the error. Our approximation is within 1 over 3,840 of the exact value of the sine of 1/2. There you go. Okay. Let's